This class has been taught continuously since the earliest record I have it was 1956, when Kevin Lynch probably taught it for the first time. This is the 34th year in which I'm teaching the class. I overlapped with Lynch for 2 years, and this is the last time I'm teaching this class. So I'm going to go through a lot of small things, details, plus some general idea about. In 1956, Kevin Lynch called this class the visual form of the city. Between 56 and 76, he changed the title to Theory of City Form. I have kept the title as the same as it was originally, well, the 1976 title.
Some funny things happened on the way to the moon as a takeoff of. Funny things happened on the way to the forum. And probably not too many people in this audience know that. Also, a particular thing that's happening this year is the 40th anniversary of the lunar landing. And we're going to talk a little bit about how MIT got involved, and let's see if we can move this along. Sputnik was about the size of a large, little maybe oversized beach ball or a basketball, and it was launched in June, I believe it was June of 1957, or later, not June. I thought I had it on the screen here, but anyhow. If it hadn't been for Sputnik, I doubt if anything would have happened in terms of the United States getting interested in the space program. So we have to have a lot of gratitude for the Russians for doing this.
My name is Joe Levitt. My group members are Ben Ayton, Jess Noss, Eileen Harvitz, Jake Barnwell, and Sam Pinto. And we're going to introduce you to the topic of incremental pathfinding. Listed on the screen now are just some of the references we used in putting together this lecture. The top three are the main references we used in developing our material on the D-star light algorithm. But also take note of the bottom reference, which is a paper done within Professor Williams' group here at MIT that talks about all pairs, shortest paths, incremental search method. So if you're interested in more incremental search methods than those we're going to talk about today, please get into this, especially if you're going to go ahead and do our piece set. These references will be very helpful to you.
Okay, welcome back to Computational Systems Biology. We have the honor today of having Professor Ron Weiss visit us, as I told you on Tuesday. He's going to talk about synthetic biology. And Ron is probably for both the Department of Biological Engineering and the Computer Science Department, and also a founding member of the Synthetic Biology Center at MIT. Thank you, Ron.
Thank you, Dave. Thanks for inviting me here. Did you mention our background? So Dave was actually advised me when I first came to graduate school at MIT. And at the time I was working on digital video and information retrieval, and Dave started getting into the business of biology. This is back in the early 90s, and I was like, this is cool stuff, it's really messy. How can you engineer with these molecules?
Okay, so what we're going to talk about in this course are materials that have a cellular structure. So they're all very porous, and typically they have low volume fractions of solids, like less than 30% solid. And we're going to talk about different types of cellular solids. So one type are honeycombs, and this would be kind of your standard hexagonal honeycomb, something like that. We're going to talk about foams, and I'm sure you've all seen polymer foams. Here's an aluminum foam. We'll talk about other sorts of foams as well. We're going to talk about some medical materials, and I brought in some bone samples, some trabecular bone samples here. I brought in a little tissue engineering sample here. And then we're going to talk about materials in nature that have a cellular structure too.
I'm not a philosopher nor a historian. This is not a class in history, although we will use a lot of information from the past as examples to give us a better idea of the present. Not that you shouldn't know history. If you're going to take this class, I would recommend a couple of books. There's no superb urban history. If there were, Harvard or MIT would teach it. It is bizarre that these two great universities don't teach urban history. It's difficult to explain. Partly it's explained by the traditions of history in architecture. Architecture, you cannot study in the arts without knowing history. It's difficult to achieve a degree in music without knowing who Mozart was. But it's very difficult to achieve a good degree in architecture without knowing who Palladio was.
Now, 1961, let's look at some of the other things. Alan Shepard's flight on May the 5th. May the 25th, President Kennedy's message to the Congress, to the world. And then on August 10th, MIT is awarded the first NASA prime contract for Apollo. NASA had just barely been created, and in response to President Kennedy's, we're going to go to the moon, they gave the job to MIT. That's pretty amazing when you think about it. And we'll say a little bit more about that in a minute. The Mars probe never flew, but the onboard computer did evolve into becoming the Apollo guidance computer. There was a computer that we had to have in our little space probe, and that did evolve into the guidance computer for the Apollo onboard computer for the lunar mission.
So today we're going to first motivate the problem, then we're going to introduce the idea of incremental search, then we're going to go into detail on the D-star light algorithm, which is a type of incremental path planning, or an algorithm used for incremental path planning, run through an example of D-star light, talk about when it is good to use incremental path planning, when other path planners might be better, and then go into some algorithm extensions and related topics and some applications in mobile robotics. So in order to motivate the problem, we're going to use a robot living in a grid world. It's at a start location, trying to get to a goal location. It can move up, down, left, or right, or diagonally, and it can only see the 8 cells around it as it's moving through this grid world.
So yeah, so after being, a non-believer, I don't know if non-believer, but just I didn't feel, it quite had the engineering capabilities yet. Towards around 96 or so is when I decided to actually kind of make the switch. And so at the time I was working around 96, I was working on this notion of how can we use what we know in biology to understand how we program computers, and especially situations where you have lots and lots of computing elements, like things like smart dust. I don't know if people have heard about amorphous computing. So back in the mid-90s or so, this notion that we would be able to embed computation everywhere was this kind of an exciting notion. And I thought to myself, how could I get inspired? And I thought, well, biology is obviously could serve as great inspiration.
So we're going to talk a little bit about wood, and I brought in a piece of balsa wood. I'll pass these around in a minute so you can play with them. This is the lightest wood, and I brought in lignum vitae. This is the densest wood. Lignum vitae is so dense that it sinks in water. And I have a couple of projects right now on natural materials, so I thought I'd talk a little bit about those too. We have one on bamboo and making structural products out of bamboo. So this is like a beam made out of bamboo, and this is a piece of oriented strand board made out of bamboo. So the same way you have like wood-oriented strand board, you can do the same thing with bamboo.
Cities occur very late in the humanoid evolution. The first tool is dated at 2.6 million years ago in the Olduvai Gorge in Kenya, found by Louis Leakey. So cities date from 10,000 years BC. We have an enormous period of time from 4 million years before Christ to 10,000 BC. During that period of time, a great deal of paleontology has been one of the transformations of the humanoid to the human erectus deals with nutrition. Until you have a tool which can make food possible other than vegetables, you'll have the capacity to take in nutritional substances into the body, which theoretically include the creation of a larger brain. So the brain size of Australopithecus, which is about 4 million years old, a post-ape animal, has a brain of about 400 cubic centimeters. You have brains of about 1,200 to 1,400 cubic centimeters.
Now, MIT was chosen for the GNNC, and the quite big question is, why? Well, Jim Webb, who was the administrator of NASA, knew Doc Draper. And this is Doc's version of what happened. Jim Webb called Doc Draper on the telephone and says, Doc, says, can you develop the guidance and navigation system for Apollo? What would you say if you were Doc Draper? You'd, yes, of course, we'll do it. When will it be ready? Well, when you need it. That's a good schedule. And how do I know it will work? And he said, I will go along and operate it for you.
So the problems we're facing, there's changing environmental conditions, we have sensor limitations, you might not be able to see everything in the environment around you, and then we have limited computation time. And the solution that we're going to explore here is to reuse data from the previous search in order to speed up the search process and continue to plan optimally. And the method we're going to use to accomplish this is incremental search. So now we're going to talk a little bit about what incremental search means. First, to show you kind of how powerful incremental search can be, this is one example of an incremental search method, incremental all pairs shortest paths, which allows you to online compute paths between any goal, start and goal location.
So welcome to Spring 2019 Machine Learning for Healthcare. My name is David Sontag. I'm a professor in computer science. Also, I'm in the Institute for Medical Engineering and Science. My co-instructor today will be Pete Solvitz, who I'll introduce more towards the end of today's lecture, along with the rest of the course staff. So the problem is that healthcare in the United States costs too much. Currently, we're spending $3 trillion a year, and we're not even necessarily doing a very good job. Patients who have chronic disease often find that these chronic diseases are diagnosed late. They're often not managed well. And that happens even in a country with some of the world's best clinicians.
Okay, so let me talk a little bit about the projects. What we do in this class is everybody does a project, and I like for you to do it in pairs, just so we have somebody to work with. I think it's nice to have somebody to do it with. And the project has to be something on cellular materials, but I really leave it pretty open-ended what the project is. It's really up to you to decide what you'd like to do. And to give you some idea what people have done all kinds of stuff in the past. So people have worked on negative Poisson's ratio honeycombs. I didn't bring any of those in with me, but you can design these honeycombs so that they have this property that when you push it this way, instead of, you make the strain smaller in this direction, it gets wider in this direction normally, but with negative Poisson's ratio materials, it'll contract in that direction. So I've had people do projects on that.
Then we go through some of the practical things that you need to know. You're going to be overwhelmed with reading. You have to develop a mature understanding of what to read and what not to read. I'm giving you an exercise. The required reading is about 1,500 pages for the semester. That's about 4 books. 4 books for a graduate student learning about cities, the form of cities, not very much. By the way, one of the reasons for the increase for the size of the reading list is the enormous expansion of material in this field. I have in front of me the 1956 references from Kevin Lynch. He totals 51 books. Mine expanded reading list is 500 books.
At the time, Bob Chilton was the head of the flight dynamics branch at Langley Field. Bob Chilton's memo, he said, the memo was stamped confidential. Nearly everything was classified in those days, and Bob gave me his original carbon copy, which I still treasure. Here we are sending men to the moon, and we had not even invented a good copy machine. Why was onboard navigation a basic requirement? Well, one of the reasons would be that the Russians might not play fair. They might jam the communication links, and we would not be able to communicate with our spacecraft.
So the whole idea of incremental search is that we're going to perform a normal graph search, just like anybody's used to, and then we're going to repeat as the robot moves through the environment, or you're executing your plan. You're going to execute the next point in the plan, the next action in the plan. We're going to receive changes from the environment, either through our sensors or information provided from the outside, and then we're going to use that information to update our previous search results instead of completely replanning, and then continue to perform that loop until you reach your goal.
So we'll start in today's lecture by giving a bit of a background on artificial intelligence and machine learning in healthcare. And I'll tell you why I think the time is right now in 2019 to really start to make a big dent at this problem. Then I'll give you a few examples of how machine learning is likely to transform healthcare over the next decade. Of course, we're just guessing, but this is really guided by the latest and greatest in research, a lot of it happening here at MIT. And then we'll close today's lecture with an overview of what's different, what's unique about machine learning healthcare. All of you have taken some machine learning course in the past, and so you know the basics of supervised prediction. Many of you have studied things like clustering.
People who have worked on tissue engineering scaffolds. Often there's people who work on food foams. So one year people worked on bread. They did bread processing. They made bread by having different amounts of yeast, different rise times, different ingredients. And they made bread. And I have a little, I like these historical things. And I have a little thing here I wanted to show you. So the people in 3032 last fall, will know that I went to England in November. And I went to the Royal Society for an editorial board meeting. But I also went and looked at their archives. And one of the things they showed me was this article, which is in the sort of original sort of archives of the Royal Society from the 1600s. And it's by a guy called John Evelyn. He's famous for writing a book called Silva about trees and wood.
When I first started teaching this class, students wanted to do papers on cities where they came from. Nairobi. There's no urban geography on Nairobi. Now there's an urban geography on almost every city that exists in the world. When we did a studio in Chandigarh in God alone knows when, in the 1980s, I think. You couldn't get a plan of Chandigarh. It was prohibited by the Indian government for security reasons. The only one that you could buy was through Russian sources via Houston for $2,000. So we did this study of Chandigarh. We had to make our own base map. Today that would be ridiculous. So if this class has a bit of a lag, it was built at a time when there were few books and material on cities was scarce.
(1961) was a long time ago. We had to use typewriters and carbon paper. Xerox had not been invented. You could watch TV, but you're not in color. They were just black and white TVs of not very good quality. You could do calculations using electromechanical machines. No personal computers or even pocket calculators. These things would cost about $800 to $1,000, and all they would do is add and subtract and divide. You could, if you spent $500 more, you could get one that did the square root, and that was a pretty amazing thing because every day, just about, the repairman would be there to fix it because it was such a complicated piece of equipment. When we'd go on business trips, no jets, we had propeller-driven aircraft, and the per diem rates were $12 a day. With that $12, I was supposed to pay for my hotel bill and buy 3 meals and do it for $12 a day. And that was plenty good, enough.
So in order to reason about a real-world environment, we first have to take that environment and convert it to a graph so we can form graph search and then do everything we're talking about. Some of the examples we're going to talk about and some of the ones we've already talked about, we're using this notion of a grid world. You can have a forward-connected graph or grid where a robot can move up, down, left, or right, basically in X or Y directions, or an A-connected graph where it can also move along the diagonals. And then here we just show the graphs associated with those, with the nodes and edges. And then you would have an associated admissible heuristic with those if you're going to perform a heuristic search.
Artificial intelligence in medicine goes back to the 1970s or sometime even in the 60s. One of the earliest examples of trying to use artificial intelligence for diagnosis was this Myosin system developed at Stanford, where the goal was to try to identify bacteria that might cause infection, and then to try to guide what would be the appropriate therapy for that bacteria. Now, it was found that this algorithm, this machine learning, this simple AI algorithm, was able to propose a good therapy in 69% of cases, which at the time was better than the best or very good infectious disease experts. Now, it also had some other elements of it which were quite interesting. So those of you who've been following the latest in chatbots might find this little present.
So if you want to do something on food foams, people have done meringues before, various things. So they look at typically changing something about the recipe or the composition or the processing or the baking, and they look at the structure. Sometimes they look at mechanical properties too. So anyway, there's a whole list of things there. You can think of other things. If you look through the books, you might get some ideas as well for projects. So what I thought I'd do next is I wanted to just kind of give an overview of what we're going to talk about, and I've got a bunch of slides. Oh, let's see, I forgot some things. Because I do that. Books, yeah. Okay, let me pass some of these things around so you get to play with them too.
The wall was the last wall of the 5 Parisian walls, was built as late as the 1820s. London's, here's a rule you can, if you don't know European history, you don't know European cities, and some of you who come from the Orient may not. The fortification of cities is more extreme as you go eastwards from England. The wall of London was a pretty miserable wall. The little bits of it left in their gates like Ludgate and so on, but basically it wasn't very much. Vienna's walls were never penetrated except in 1683 by the Ottoman Empire. You don't need to know all of these details, but you have to understand the conceptual structure.
In 1961 was a vintage year. A lot of things happened then. There they are. In January the 26th, the first multiple flyby orbit of the planets was determined by going from Earth to Mars via Venice. You go from Earth to Mars to Venus, Earth to Venus to Mars and back to Earth, all in one launch. And that was discovered by me in January the 26th of 1961. I have to emphasize that that date is very important because there was a lawsuit by some body whose name I must not mention, who brought suit against me for because he said he did it first, but he didn't really. In the spring of that year, the first offering, that is the first class in Astronautical Guidance, is what my course used to be called until it was changed to Astrodynamics. On April the 12th, Yuri Gagarin flew 3 orbits of the Earth
So what incremental search methods exist, now that we've kind of talked about what they are and what we can do with them. So the whole idea of this slide here is to show you that incremental search can be used across many domains. It's not just specific to path planning. It's used in temporal planning to determine temporal consistency. That can be used in propositional satisfiability to instead of every time you're trying to determine or updating another algorithm, you can use your previous results. And but one we're going to focus on today is D-star late, which is specific to mobile robots. But the ideas and concepts we're going to talk about there are applicable elsewhere, and you can use to help you learn about and expand your knowledge in other areas of incremental search.
So the ideas of how AI can really impact medicine have been around a long time, yet these algorithms, which have been shown to be very effective, even going back to the 1970s, didn't translate into clinical care. A second example, also equally impressive in its nature, was work from the 1980s in Pittsburgh, developing what's known as the Internist 1, or Quick Medical Reference System. This was now used not for infectious diseases, but for primary care. Here, one might ask, how can we try to do diagnosis at a much larger scale, where patients might come in with one of hundreds of different diseases and could report thousands of different symptoms, each one giving you some view, noisy view into what might be going on with the patient's health.
So you can think of the cells as small compartments, that kind of makes sense. And he kind of very modestly says, I no sooner discerned these, which were indeed the first microscopical pores I have ever saw, but methought I had with the discovery of them perfectly hinted to me the true and intelligible reason for all the phenomena of cork. So he's saying by looking at the structure of cork, he thinks he understands everything about the properties of cork, very modest. But in fact, this is kind of the foundation of material science. So material science is all about looking at the structure of materials and trying to say something about the properties and the behavior of the materials. And that sentence kind of sums that up. So that's why I like that sentence.
Cities were always clearly demarcated between town and country. It took until Renaissance Italy for nature to be introduced in the walls within the womb of the city. The Romans used to say hunc, I think hic or hunc sunt leones, they are lions. The world outside was, the walls was a world of treachery and difficulty and fantasy. Many ideas about cities which are as complex as that idea, but the antagonism between country and city still lasts today. President Obama was elected because of the majority that he had in cities. The Democratic Party is an urban party by and large, although this has changed significantly as the size of cities has changed, and as the demarcation of polling districts has changed. But we'll talk about this distinction between country and city, and in the third class where I'll deal with the organic model.
October the 13th, the American Rocket Society had a meeting because Kennedy said he wanted to know what progress had been made. And so we had a space flight report to the nation of all the stuff that we were doing. Later, on November the 21st, Draper, who had said to Jim Webb that yes, he'd make sure it worked because he'd fly it, he volunteered formally to be an astronaut. And then I thought of this much later. December the 23rd was Christina Schu's 100th birthday. Who in the world is Christina Schu? My grandmother. So in 1961, a lot of things happened Here is the first round trip to Venus. We were a little discouraged by taking 3 years to get to Mars and back home. So we said, well, maybe we could go to Venus a little and return in less time. And as a matter of fact, you can.
So now, let's say the robot moves. We did an update to the environment. There's a bunch of changed edges. And now breadth first search, as you can see, is going to have to expand pretty much the same number, if not more nodes than did on its previous search. And A-star also is going to expand about the same number of nodes as it did previously. The incremental search method using breadth first search, by using the previous results, reduces significantly the number of nodes that need to be expanded. And then ACE, lifelong planning A-star, the incremental search plus the heuristic search, reduces that number by even more.
Now, you might want to go to a different domain outside of primary care. And again, one has to spend a huge amount of effort to derive such models. As new medicine discoveries are made, one has to again update these models. And this has been a huge blocker to deployment. I'll move forward to one more example now from the also from the 1980s. This is now for a different type of question, not one of how do you do diagnosis, but how do you actually do discovery? So this is from an example from Stanford, and it was a really interesting case where one took a data-driven approach to try to make medical discoveries.
Often in nature, the cellular material appears in combination with some solid material. And so it's sort of a structural component. And you can see sandwich structures in nature, leaves and skulls. You can see materials that have density gradients. Palm stems and bamboo are examples of that. And you can see materials that have cylindrical shells with compliant cores, and things like plant stems and animal quilts are like that. So that's kind of the range of materials that we're going to talk about. And one of the interesting things about cellular materials is that you can make cellular materials out of almost anything now, and there's really a huge range of materials and lots of different applications for this.
Look, I'm not a historian, and this is not a class in history. It's a class in deriving ideas from a number of sources and arguing them with you. I have no, other than a lot of time having been spent teaching and preparing for this class, and a lot of external experience practicing in cities all over the world, I have no golden formula for the truth. I don't claim to have that. I'm not sure that I believe anybody who says they do. I'm not a theist, and I'll come across quite often as an agnostic, if not an atheist, with regard to truths of religion. Jerusalem was only been the capital of a city, of a country, twice. Once during the period of the 10th century, during the Crusader occupation, and after 1948 with the advent of Israel. Jerusalem, which we'll do in great detail in one case study, is subject to an enormous number of philosophical and interpretations of history.
Here's the textbook for the graduate course in astronautical guidance. The name of the book is Astronautical Guidance. The diagram, if you take my course, you'll find out how to navigate in space by making measurements of angles between stars and near bodies. And so that little diagram was on the fly leaf and is also on the inside of the book in color. Now, when the book came out, we were having a heavy load of important visitors, and Doc said, he took my book and he said, "Batten," he says, "I want you to buy a lot of these, and I want you to autograph them. We're going to have important people here." And sure enough, let's see who the important people are. Well,
So I'd like to just remind you of several concepts from A-star first, because it's easier to introduce them in that context, and then we'll modify them a little bit. So Joe mentioned before that for A-star, we're searching from a start node to a goal node. We're sorting the nodes in our queue by total cost, which is the sum of what we're called G, which are our cost to go, or cost to get to a single node, and our heuristic, which is the cost to get from a node S to the goal node, here S. Now, what we don't usually consider with A-star, but is very important for D-star, is how we distinguish between ties, when two different nodes on the search queue have the same total cost. So here what we're doing is we're introducing a couplet, which consists of two values.
MIMIC contains data from over 40,000 patients in intensive care units, and it's very rich data. It contains basically everything that's being collected in the intensive care unit. Everything from notes that are written by both nurses and by attendings, to vital signs that are being collected by monitors that are attached to patients, collecting their blood pressure, oxygen saturation, heart rate, and so on, to imaging data, to blood test results as they're made available, and outcomes, and of course also medications that are being prescribed as it goes. And so this is a wealth of data that now one could use to try to study, at least study in a very narrow setting of the intensive care unit, how machine learning could be used in that location. And I don't want to underemphasize the importance of this database, both to this course and to the broader field.
Foams are also good at being thermal insulators. They have a low thermal conductivity, and that's because they're largely made of gas, and the gas has a lower conductivity than the solid, so that gives them low thermal conductivity. And they have a large surface area, and the smaller the pore size, the bigger the surface area per unit volume, and that makes them good for things like carriers for catalysts, and that's why they're used for these catalytic converters too. Okay, so here's some examples of cellular materials in medicine. So here's some examples of trabecular bone. Trabecular bone exists at the ends of your long bones, so say in your hip or in your knee. It also exists in your vertebrae, in the middle of the spine and the vertebrae there. It also exists in your skull.
Let me just say something which I hope you'll remember. In one of the evaluations of this class, which is done every year, there was a question from the students as to why they didn't ask more questions. And one of the number of answers said, the professor knows too much. My response is, would you prefer to be taught by a professor who knows too little? That's a stupid response. Please just don't feel because I have had 34 years of experience teaching this class that you should understand it all without question. I feel free to diverge and choose opportunities to say things which come to me for the first time. That's the way I think. I would like you to think in the same way, even if you might get irritated by my presumption.
MIT awarded the first Apollo contract, and here was the team. We have Jim Webb, one in the center, and to the left is Hugh Dryden. He was the deputy administrator, but he passed away in December of 1965. And then there's Bob Siemens, the associate administrator. He was promoted to deputy administrator. And Bob Siemens, as you're well aware, passed away. I was very happy that when I gave this talk at this time last year, Bob Siemens came. He had not heard it before, but he came and listened, and I was so pleased that he was there, but he passed away shortly thereafter. MIT was chosen. Why? Well, Bob Siemens' book, Aiming at Targets, says, that doesn't give you much information. He just says when the decision was made to go to the moon, the Draper Lab got the contract for the navigation system.
Firstly, we want to initialize all nodes as unexpanded, and what exactly it means to expand a node later, I'll cover. And then we're doing a best first search from the goal node to the start node until the start node is consistent with its neighbors. And I'll again say what that means later. We then move our start node to the next best vertex, essentially moving along the plan, or node, moving along the plan that we created. And then we have to see if any of those edge costs change. We track how our heuristics change, and then we update the source nodes of those changed edges. And we essentially repeat this process until again we've converged to a solution and we keep moving.
So right across the street at the Broad Institute, there's a team which is creating all of the software infrastructure to accommodate this data. And there are a large number of accruement sites here in the broader Boston area where patients, or any one of you really, could go and volunteer to be part of the study. I just got a mail, I got a letter in the mail last week inviting me to go, and I was really excited to see that. So all sorts of different data is being created as a result of these trends that I've been mentioning. And it ranges from unstructured data like clinical notes to imaging, lab tests, vital signs. Nowadays, what we used to think about just as clinical data now has started to really come to have a very tight tie to what we think about as biological data.
People are starting to think about using metal foams for coatings of orthopedic implants. So one of the issues with implants is that, say you have a hip implant or a knee implant, you remove the bone that's pre-existing, and then you replace it with some sort of implant. Typically the implant has a stem that fits into the hollow part of the bone, and then has a sort of joint piece to it that fits into the joint. And you can get some loosening of the stem in the remaining bone. And one idea is that you use porous coatings to minimize that. And right now, typically what they do is sinter beads, metal beads, onto the stem. And another idea is maybe you could use a metal foam, and these are some different types of metal foams that people are looking at.
There is no single theory of city form that exists. There's no absolute theory. There are many theories. And there are preferred theories as opposed to city theories. There are many, many problems. Robin Dunbar's theory about 150 people has been taken up, and corporate firms have divided their manpower into groups of 150 people based on Dunbar's studies. We're not going to do something as silly as that. Reading those two pieces by Kevin Lynch generated in this class through discussion.
George Miller was the associate administrator for manned spaceflight, and he was a NASA person, and he was very much concerned with the computer software. In fact, he had just come from he was in charge of the software for the Mariner 1 spacecraft to Venus, which was launched in 1962, and it went off course due to a software error. There was a missing minus sign in the code. He had this minus sign framed and hanging in his office. Do not take for granted that you've got to check everything to make sure that it's going to work. The astronauts used to come and visit us, and in the fall of 1966 we had 6 astronauts. They're all sitting down there in the front row, and we had them autograph these. And then there were people in the back were the ones that are working on the job.
So now, our heuristic is the number of nodes away from that green node. And we're keeping the same items on the queue from before. but we also have to update the key modifier. So now what happens is an obstacle appears. So there's an obstacle at C that the robot can now see because it's moved closer to node C, but it couldn't see it before. So now we're gonna indicate that by keeping all the edges but changing their weights to infinity. And that means that the robot could try to get to C, but it won't ever get there. So what we do next in the algorithm is we're going to update all of the RHS values associated with the source nodes of these edges. In this case, the edges go both directions, so it's all 4 of these nodes are affected by the infinities.
Laboratory test results are standardized using a system called LOINC here in the United States. It's again, every lab test order has an associated code for it. I just want to point out briefly that the values associated with those lab tests are less standardized. Pharmacy national drug codes should be very familiar to you. If you take any medication that you've been prescribed and you look carefully, you'll see a number on it, NDC 0015347911. That number is unique to that medication. In fact, it's even unique to the brand of that medication. And there's an associated taxonomy with it. And so one can really understand in a very structured way what medications the patient is on and how those medications relate to one another.
Imagine you have a drinking straw, and now you put foam in the middle. It's going to be harder to get it to kink like that. So that's what the plants are doing. Animal quills do the same thing. That's a porcupine and a hedgehog quill. And all of this stuff is in these 2 books. So it doesn't really matter to me if you go out and buy the book. I don't make much money on these books. So this is not an income-producing thing. But those are the books that all these pictures have been taken from. All right. So I think that's my sort of introduction to the class. Are there any questions about sort of how we're organized or what we're going to be doing? Are we good? Yeah, it's okay? Okay. So then I think what I'm going to do for the rest of the time is start the next section of the course, which is on processing of cellular materials.